that will be network error. You have to just say, this is the stop the video.
Hello? Hello? Today, starting Workspace analysis. Okay. Good morning, everyone. Today we will study workspace analysis. Okay, what is workspace analysis? If you try to understand, you have already studied something called as your manipulators, your arm manipulators and all. So today we will be dealing with the workspace of that manipulators. Okay, so what does workspace analysis consist of? Workspace analysis actually is the area in which the robot can do useful work. Okay, so the area in which your robot arm can move and do some useful work of picking up, placing operations is called workspace analysis. Now in this direct kinematics, we find position and orientation of tool and gripper with respect to the base. This was given in your 4x4 composite coordinate homogeneous matrix, and it was also called as the arm matrix. And it was given by T raised to tool and T raised to tool by the base. Okay, so transform raised to the tool by the base. We used to solve direct kinematics using DH algorithm, and in inverse kinematics we found out set of variables which is used, which will satisfy the same position and in orientation. That is a number of way to find out the find out the solutions to reach a point P using analytical, geometrical and numerical method. We used inverse and direct kinematics formulation to solve higher level problems in the 3D space, that is to plan the trajectories in the 3D space. Now we will perform detailed analysis. So in between this direct kinematics and inverse kinematics, the robot comes into picture. What the robot comes into picture, this robot motion consists of paths and trajectories which are existing in the workspace of the robot. In this chapter, we'll be doing detailed analysis of the robot workspace, and later on we'll go to trajectory planning using this workspace. So, what is a robot workspace? As it is written, the robotic manipulator consists of arm and base and end effectors, and it is used to do useful works like drilling, painting, etc. Now, this useful work is done in the particular workspace of a robot. So, if you want to define workspace, so what will be workspace for you? Workspace is the work area, or the area in which the robot robotic influence is experienced, or the area in which it can do the pick and place operations. You can even say that this is the area in which the robot can do useful work, and in which the robotic manipulator is free to move. Okay, so the area in which the total workspace envelope of a within the workspace envelope of a robot. That is, suppose if this is my robotic arm, so my robotic arm has a degree of freedom and I can move only in this way, that is from this end to this end. So this is the area covered under this zone is my workspace. Okay, the freedom in which my end effector can move and perform some task is my workspace. So at present my hand is moving from this end to this end. So the degree of freedom is this much, and so this is my work envelope. Okay. Now combining robot view from the side, that is elevation, and from the top, that is the plane, we calculate the total workspace. Okay, the end of the robot, the end in which the robot arm can reach, the workspace can be 2D, so it is represented by R raised to 2, and the total workspace can be 3D also. It can be R into N depending on the degree of freedom which is given to the robot. So robot classification is based on workspace. Okay, now workspace, how will you divide, or what are the types of workspace, how will you analyze that? So based on the sequence joins used by the major axis, you are classifying the workspace into 3 categories. Okay, that is, what is the workspace types? That is, you have 3 types of workspace envelope. So first is your total workspace envelope, or the gross workspace envelope. Then you have, you can call it as the just the work envelope. Fine. Then you have JSWE. Okay, so the total workspace envelope is denoted by TWE. The joint workspace envelope is denoted by JSWE. And when we have Dexter's workspace envelope. So workspace envelope is nothing but the locus. Okay, the locus of all point, which is, now see, if it is moving from this end to this end freely, so the locus of all the point tracked by the tip of the end effector or the true gripper in the 3-dimension Euclidean space is the boundary, forms the boundary of the workspace. Okay, so it is the locus of all the points P, okay, which is lying, which are reachable in R3 by the tool tip, or it is the curve in which the curve in the 6th dimension of the tool space. Okay, so this is how your workspace is defined. Okay, so now what are the factors your workspace envelope depends on? The factors on which your workspace envelope depends on is the robot's physical configuration, the geometric link parameters, the type of the robot, the degree, number of degree of freedom, the type of application, the limits of the robot joints and its movement, the nature of the work. Okay, so this is what these are the factors which are taken care while calculating your robot workspace envelope. So here you can see in this PDF you have after the definition joint workspace envelope. Okay, so I told you that our workspace envelope is of 3 types. That is, first is total workspace envelope. Then you have gross workspace envelope. Total workspace envelope is also called as the gross workspace envelope, or just the work envelope. then you have something called as joint workspace envelope, and then you have got something called as Dexter's workspace envelope. So what is this total workspace envelope? Total workspace envelope is denoted by the symbol Y, and it is defined as the locus. I told you now, my hand can move from this end to this end because it is connected out with a ball and socket joint here. And imagine this to be the gripper of a robot, this as a two-handed gripper of the robot. So suppose if the robot is moving from this end to this, just excuse me, Q is a subset of R raised to N. Q came in, which is less than equal to CQ, less than equal to Q max. Now, what is joint space envelope and how it is denoted, why it is denoted by Q? So symbol Q is defined as the workspace envelope that is tracked joints in the joint space R raised to N. Now see, Rn is given out here, but normally we take 3 dimensions into consideration, so we will denote that by R raised to 3. So a set of all values that can assume in Q in the joint space. When workspace envelope is used with is viewed within a work frame, the joint of the joint space, the shape of JSW, which is obtained by capital Q, is a convex polyhedron in the given space. Means if you try to calculate JSW, that is joint space work envelope, it will be nothing but it will be in the form of a polyhedron which is in the given space. That if it is 3D space, so it will be R raised to 3. If it is 4D, then it will be R raised to 4 up to R raised to N. So if you can see the equation out here, that is this equation Q, okay, in that Q is equal to Q, small q belongs to R raised to N, Q min less than equal to CQ to Q max. So what is this Q? Q is the joints workspace envelope, N is the axis or the DF of the robot, small q is the joint variable, kth joint. It is actually Q raised to K, which is not printed out there. Your small q is nothing but it talks about the kth joint variable. Now, see, in a robot, we have 2 types of joints. The one joint which linearly moves in and out, and one joint which rotates in 360 degree. Okay, so your joint may be prismatic or revolute. Fine. So rotatory, how will you represent? If it is a rotatory joint, QK will be equal to theta K. Okay, and if it is prismatic, if it is a linear one, then your QK will be equal to dk. Right? So R raised to N is the joint variable. It is a n-dimensional joint space in which all the joints are situated. So QK belongs to Rn means all the joints Q are situated in the joint space R raised to N. That is, they belong to the space. Whatever joints QK which belong to the space R. Okay. Now QK min and QK max. Okay. How will you judge this limit? Are the minimum and the maximum limits? Okay. Normally QK, if you similar to a human hand, that is elbow joint has got minimum 0 degree to maximum limit of 130 degree. Assume this can be approximately 130 degree. Okay. Now C is what? CQ, which is written out here. So CQ is the joint coupling matrix. Okay, a joint coupling matrix. Now this matrix should have a size. So what will be the size of this matrix? It will be M into N. Okay, or M into M or N into N. Okay, each joint is coupled to the other joint using a joint coupling matrix. Means if this is the joint which is coupled to this joint, then it is coupled using a joint coupling matrix. The simplest value of the joint coupling matrix occurs when C is equal to the identity matrix. Okay, so whenever there is inter-existing coupling, that is inter-axis coupling between the joints, that time you will have C which is not equal to the identity matrix. Normally C is equal to the identity matrix when they are independent, when there is no inter-axis, okay, inter-axis coupling. That is one joint does not depend on the other joint at all. Okay, all the joints are independent of each other. That time we will have what? We will have the value of C will be equal to value of I, that is your identity matrix. Okay, normally there are no global or coupled angles, like if you see the SCARA robot, C is normally equal to the identity matrix or the square matrix. Fine. So now coming on to DWE, that is Dexter's work envelope. Dexter's work envelope is denoted by a symbol YD, and it is the locus of the reachable point from the arbitrary tool orientation, such that this origin is reachable from all the orientations or the Dexter's or the work envelope for any arbitrary tool position or orientation that is reachable from all the directions. Okay, so now what you will consider the elevation plane and all the directions in which the robot is. So the work envelope which is able to be reached from all the angles. A number of arbitrary tools are possible within the total work envelope. As a result of this, we get family of infinite numbers of Dexter's workspace envelope which are lying inside the total work envelope. Okay, so all small envelope which are lying inside the total workspace envelope are called as Dexter's workspace envelope. Right? So Dexter's workspace envelope are more practical than other workspace envelope because they are associated with one particular tool position and orientation. Note that there is only one total workspace envelope, which is whereas there are infinite numbers of DWE. See, don't get confused. TWE is the total workspace envelope. DWE is the Dexter's workspace envelope. TWE is subset is DWE. Okay. So now you are seeing something in the figure given out here is a work envelope of this is actually called as a link coordinate of link coordinates of 5 axes Rhino X3. Okay, the robot shown out here is Rhino X3, and the diagram which you are seeing is the link coordinate of 5 axis Rhino X3. Okay, so this is a 3D view of it. Fine. Now, more clear picture I will send and put it with the table. See now, in Rhino is a 5 axis articulated robot. Okay, all the 5 angles are given by named as BSEPR. Okay, what is the name of the angles? It is BSEPR. Now, BSE is the major axis. Okay, BSE is the major axis, and PRY is nothing but the PR is the adjoining angles. So, base, shoulder, elbow, BSE. Okay, now there are 5 number of joints. If you see here, you have 1 joint here. Okay, you have another joint here. You have the 3rd joint here. You have the 4th joint here. You have the 5th joint here. And to the 5th joint, what is attached? Here, tool is attached, which can be a gripper. Okay, now see. If you see the link coordinate diagram shown out here, you will be able to find out the minimum and the maximum bounds of P. That is, see, what we are interested is, we want to find out the work envelope or the area covered by this point P. Okay, so we have to find out what? We have to find out the maximum horizontal reach. Okay, suppose if this is connected to this. Suppose if this is your tool tip, and imagine a last P, point P. Okay, if this is your tool tip and this is the point P of the tool tip. So what I'm interested is the maximum horizontal reach of this tool tip and the maximum vertical reach of this tool tip. Okay, so this and this is what we will be finding in using this link coordinate axis diagram. What we'll be getting through that? We will be getting the workspace envelope through that. Okay, so now if you see the WSA has, can be found out using this link diagram. Now the combinations, that is the maximum and the minimum horizontal reach, which is taken into consideration the number of joints is provided by the manufacturer. See now how far it will go, how far a robot will reach is dependent on the joints which it has. So how will you find out? Now this is taken from the textbook Fundamentals of Robotics by Robert Schilling. Okay, so the first step to find out the workspace area is to find out the expression for tool configuration vector, that is WQ. Okay, this cannot be directly found. There are certain steps. It is written out here, but there are certain steps. Now see, what happens is the combination of all the maximum and the minimum. Okay, maximum and the minimum reaches, that is a freedom, the distance reaches, gives rise to what? The workspace area of the robot, and is the area in which the Rhino can do some useful works. Now if you see this diagram properly, the above diagram, see, you can see this. Okay, so you can see it is connected using this many joints. So using this tool, you are going to do some particular work. Either you can pick up, place, so you have to compress it, you have to release it, do certain joint. Now see, your base, okay, base is a rotatory joint, okay, it has a angle theta, because see, it is given out here, it is rotatory, okay, it is rotating. Okay, and it is rotating by an angle what? It is rotating by an angle θ1. Okay, and the axis of rotation is vertical. So it will be rotating like this. Means from this angle to this angle. Like this it will rotate. Now your shoulder. Go to the shoulder. Okay, shoulder is jointed out here. Now see the axis of rotation of the shoulder. Shoulder is not rotating. See, your base will rotate like this vertically, but the shoulder has a angle theta 2, which is making it rotate like this. Okay, the angle of rotation is horizontal out here. Okay, so the axis will be this side. Fine. Now envelope. Your elbow. This is the elbow out here. So elbow has the third angle. Okay. Again, it is a rotatory joint. It is rotating in 360 degree. Okay. Now after that, you have TP, tool pitch. Okay. This is your TP joint, which is called as abbreviated as TP in the table of link coordinates, but it will be see, I forgot to paste that table of link coordinates out here. I'll compile it and repost it on the CN. Now see, you have TP, which is given as tool pitch. Now tool pitch has a rotatory angle theta 4, and see the moment, the angle of the moment is given out using this directions of the arrow. Okay, now you have TR. Okay, point the fifth joint, it is TR, that is tool roll. Tool roll will be responsible. This is your fifth joint, and it is again a rotatory angle, and it is given by theta 5. Okay, so it is, the rotation is downwards. Base is vertically upwards. Tool point, the rotation is downwards. Please, students, take a note of these positions, because these positions play an important role in finding out something called as kinematic parameter table. Okay, and from that kinematic parameter table, we will be finding out something called as the final matrix. Okay, we will be finding out the final matrix, which is given out here. This one. Okay, now you came across how many joints? Joint from J1 to J5. Okay, that is first base shoulder. Okay, then you have an elbow, then you have tool pitch, then you have tool rolls. Okay, so you have J1 to J5. Okay, all the joints are rotatory. Then Q, small Q1, we will have Q1 to Q5. Now what is this small Q1 to Q5? This small Q1 to Q5 is nothing but the 5 joint variables. We had joint which are rotatory 5 joints, so that's why we will have 5 joint variables. Okay, and L0 to L5. What is this L0 to L5? That is the 6 right-handed frame coordinates. Okay, see. Okay, we have how many joints? 1, 2, 3, 4, 5. So we have 1, 2, 3, 4, 5 Qs. Okay, and we will have so many R6 RHOC. That is right-handed orthogonal coordinate frames. Okay, so the vector of this joint, the vector of all these joints, 1, 2, 3, 4, 5, is Q. Okay. And the joint distance is given by D1, D2, D3, D4, D5 respectively. The angles are given by theta 1, theta 2, theta 3, theta 4 respectively. Now see, if you try to understand, Q will be equal to all the thetas. Okay, Q will be equal to all the theta, which will be equal to theta 1, theta 2, theta 3, theta 4. And from that, we get this expression. See, the joint variable of the minor axis used to orient the tool pitch is given by theta 4, Q4, and the tool angle is given by Q5. The tool angle has no, tool roll angle has no effect on the tool tip position P. However, the tool tip position changes the angle pitch Q4. Okay, so the final is measured by the workspace envelope. The global tool pitch reached by the angle 234 is measured relative to the XY plane or the horizontal work surface. So what is the expression consisting of WQ, which is equal to, which is also called as TVC, or TVC of the tool configuration vector of your Rhino. Okay, and it is given by WQ is equal to W1, W2, W3, W4, W5, which is equal to P1, P2, P3 expression Q5 by pi. Okay, exponential Q5 by pi, exponential Q5 by pi, or of R13, R23, R33, and which is equal to C1 A C2 A2 C2 plus A3 C3 C23 plus A4 C234 minus D5 235. Then the second row is S1 A2 C2 plus A3 C23 plus A4 C234 D5 S235 D1 minus A2 S2 A3 S3 A4 S34 D5 C35, and the expressions minus e raised to Q5 pi C1 235 minus Q5 pi S1 234 minus Q5 pi C2 C234. Okay, so this is how we find the tool vector configuration of WQ. This is the first step. After that, we find something called as the joint space envelope. Joint space envelope, workspace envelope. The joint angles are constrained to lie in the joint workspace envelope of Q of a robot, and is given by Q equal to QK belongs to R raised to 1, QK min, CQK up to Q max. Okay, so 1 less than equal to K less than equal to N, where N is what? N is the degree of freedom. So here we have 5 joints, so we have 5 degree of freedom. K is the particular joint in your robotic arm. Okay, and it is given by Q1, Q2, Q3, Q4, Q5, Q23, Q2, 3, 4 is less than equal to C7 into 5, Q1, Q2, Q3, Q4. This is the vector of the Q, which is like the minimum, and this is the maximum. Okay, so the angles, which is, how will you try to represent it in the form of a matrix? So this is like this. See, pi minus 3 pi by 4, pi by 4, 5 pi by 4 minus pi, 3 pi by 4, 5 minus 5 pi by 4. This is the matrix, which is your identity matrix, and then you have this. Okay, this is same pi, which is positive and negative out here. Okay, from the above equation, the conclusion comes that there is no constraint on the base angle of Q, as it is the range of one complete cycle from minus pi to pi. Means, see, joint constraint on the global, see, joint constraint consists of, when we take joint constraint, we consider both joint angles and the global angles, that is angles which are on the joints, and the coupled angles, the angles which we talk about when we have the links. Okay, so now if you take the angle of the base, if you consider the angle of the base, so what will happen? Base is the first joint, so it is Q1. Q1 has the angle what? Theta 1. Okay, there is no constraint on the base, there is no limitation to the base, because base is fitted to the, it is fixed, and but still it is given a, you know, it is fixed to some space, but it has a 360 degree full rotation. Either it will start from +5 to -5, assuming the position of the point P changes with respect to Q1. Okay, if it is, suppose, if this is the base and this is the shoulder, okay, elbow joint, and here is a tool tip. Fine, assume this to be the tool tip. Now, because the base is rotated to the right hand side, the tool tip is here. Now suppose it has 360 degree of freedom of rotation. So if it is rotated now, this will rotate from this end to this end and the tooltip will be on this side. So the position of this tooltip P, point P, depends on what? On this base also. So shoulder. Now shoulder is theta. What? Shoulder is where? Shoulder is here. Okay, shoulder is in between. So between the base and the elbow. So shoulder constraints are present. Okay. As the angle of the shoulder changes, the angle of the position of P changes. Again elbow. Okay. As the angle of the elbow changes to the maximum and the minimum limit, the P position of the P again changes. Tool angle, that is tool angle which was present, tool pitch which was present after the joint after the your elbow. Now if that angle also changes, your position of this tooltip will change, because this is elbow out here, you have tool pitch out, you have tool roll out here, and you have the pitch, tool gripper out here. So you have one rotation out here, you have one rotation out here, and you have one change in the position of the what? Your point P, the gripper axis of operation will change. So these are the factors which affect these angles. Okay, these angles are joint angles as well as the coupled angles. These angles cause effect on the position of the tooltip. Now see, we have 5 joints. Okay, we have 5 joint variables, we have 5 angles Q4. What is this 2, 3? Okay, what is this Q2, 3? Your Q2, 3 is 0, is equal to 0 when the forearm is horizontal. Okay, why? Because Q2, 3 is the global elbow angle. What it is? Q2, 3 is nothing but the global elbow angle, and Q2, 3, 4 is the global total pitch angle. What? Global total pitch angle. Now, when it is horizontal, it will be 0. When it is vertical, it will be minus pi by 2. Which angle? Q2, 3. When it is horizontal, because your elbow is connected like this, it is already under, the angle will be equal to 0. It is with the plane. When it is vertical, you are taking a pi by 2, a 90-degree angle. So it is minus pi by 2. Similarly, if it is, let us go back and see the joint. See here. Okay, tool pitch angle, this angle, this angle, this angle, and I'm talking about this angle. The angle, the global elbow angle is given by 2, 3. Okay, here, the angle here, which it takes, is given by Q2, 3. And the angle which is taken here is given by Q2, 3, 4. Okay, total global total pitch angle and global total elbow angle. Okay, so this is how you have to take that these angles are also included in the joint constraint. Okay, and it is represented out here. It is in the next matrix. Q3, Q4. It has a variable out here also, S234, S234, C234. Okay, so this is nothing but the total angle. Fine. Now, that's why we have 5 joints, but we have 7 variables in the equation. In the vector. Okay, so this is your joint variable, joint space work equation. Right. Now, there is no constraint which has to complete a cycle of -1, complete the total tool angle range Q5, that is the angle of the gripper, ranges over from one complete cycle, that is minus pi to pi. The constraints on the global angle, that is the limit of orientation of the, it is based on the orientation of what the forearm, and it is related to the work surface. Now you have something called as the reach constraint. What is this reach constraint? Okay, now reach constraint is what? Reach constraint, you can see in the diagram given out here, this is something called as a reach constraint. Now what is this reach constraint? It is a one line diagram of rhino X3 with its projection of links along the horizontal and the vertical directions, means one line diagram of reach of robot. Suppose this is the, imagine this to be the arm of the robot, and the reach of the robot is in horizontal spaces, the distance of the link is this much, and vertical space is this much. So if I try to draw single line diagram of the reach, it will be represented as this. So this is the reach constraint diagram. Okay, this one. This is the evaluating reach constraint diagram. Fine. Now coming back to the diagrams. Now each variable has an independent person, but the total workspace which we collect is means it is a summation of all these joints movement. So if I have a rhino X3, now referring to the earlier diagram, if you refer to this diagram, excuse me, just a moment, diagram number, yeah, please see this diagram out here. Okay, in this you can see the link of the upper arm. Link of the upper arm is given by A2, A3, and the link of the lower arm is given by, I'll just maximize. The link of the lower arm is given by, just a moment, I'll magnify it more, is given by A3, okay, upper arm is A2, forearm is A3, okay, and see, if you go down, see this diagram, your B1 out here, B1, this distance B1 is the horizontal distance between the shoulder and the pitch frame. Okay, and horizontal components. Okay, horizontal components will take care of what? See, this joint, yeah, this distance and this distance. Okay, this distance and this distance. Okay, so when B1 is 0, B2 will be equal to A2 plus A3. Okay, I'm repeating it. When B1 is equal to 0, your B2 will be equal to A2 plus A3. Okay, so horizontal components is based on two links, that is A2 and A3. Vertical components are again based on the L1 and L2. So link components A2 and A3 are still active. Okay, A2, A3 will be still playing a role out there. So when your B2 is equal to 0, B1 is equal to A2 plus A3, and it will. So if you try to write the equation of the radial distance from the origin of the shoulder, your B1 will be equal to something called as, see, if you see here, excuse me, it's not clear. See here, oh God. talking about is, therefore, if we try to write an equation of the total radiation distance from this from the origin of the shoulder frame from this end to this end, that it will be equal to B1 equal to A2C2 plus A3C3, and B2 will be equal to A2S2 plus A3S3. Okay, now if we take into consideration the diagram which is given down to, because it is not clear out there. Now it will be clear out to us. This is your joint 2, this is your joint 3, and this is your joint 4. This is the distance B resultant distance, and this is the distance B1, and this is the distance B2. Okay, we were finding out the equation B1 equal to what? A2C2 plus A3C23. Okay, and B2 is equal to A2S2 plus A3S3. Now see, if we get the resultant which is from out here, it between the two links A2 and A3 are straight, and the reach is, it is given by in the form of a Pythagoras theorem. If the resultant is in between, and it is like, and A2 and A3 are straight, the reach constant is given by B1 square plus B2 square is equal to mod of B square. Therefore, B1 square plus B2 square is equal to A2 plus A3, fine, which is gives us the distance from the origin of L1 frame to L3 of the coordinate frame cannot be greater than A2 and A3. So whatever distance it takes, it won't be greater than A2 and A3. Now, different reaches in the rhino. From the above equation of the reach constant, the maximum value of P1 will occur when B square plus B2 square is less than to A2 plus A3 square, and P2 is equal to 0, and P3 is equal to D1 plus D2 will be minimum. Therefore, the upper bound on P1 for the given two orientation of Q2, 3, 4 is mod of U1 plus A2 plus A3. Now, limitations on P2 is that once the first coordinate of P is selected from the maximum, P2 automatically will be equal to 0. Therefore, the robot is in the XZ plane, and the constraint P3 gets reduced to distance D1 plus U2. Limits on P3 is once P23. Now, Q23 is what? The tool pitch angle will be dependent on P1 and P3 selected. Bound on P3 reduces to P3 should be D1 plus U2. Now, we will be studying something called as workspace fixtures. Okay, so workspace fixtures are accessories and add-ons on the robot. The fixtures form a part of the robot to perform a particular task. Workspace fixtures are used in workspace of a robot, and our part feeders are of different types. So part feeders, second type is transport devices, and third part is your part holding devices. So what is this part feeder? Part feeder is the device which is used to feed parts to the robot. For the object to be successfully grasped by the robot, the part must be presented to the robot in the manner to the tool configuration realized by the manipulator. The part feeders are usually concentrically arranged around the base of the robot near to the outer boundary of the work envelope. Part feeders are activated electromechanically, and electrically. Part feeders are activated based on the reach. Now see, Part feeders there are two type of reaches in Rhino. Okay, so Rhino, this is just a moment. This is electrically. Part feeders are electrically, basically vibratory bowl devices, and those are activated electromechanically are gravity fed devices. See, this is concentric layer of a multiple part feeder, and gravity fed to the feeder. Okay, transport devices are normally used to move the part from one robotic work cell to another robotic work cell. Conveyor belts and carousel are the example of transporting devices. Conveyor belt and carousels are special part feeder. They transport between robots from one robotic vessel to another linearly. Conveyor belt transport the part horizontal either from left to right and right to left in only one direction. They are driven by electrical motors. See, like this conveyor belt. Okay. Carousels are rotatory transport devices. It transfers parts back and forth. Okay, between two or more. No, in between two robots. It consists of a rotatory table with a center pedestal. See, like this. So this is a form. This is the carousel. Here you have robot 1. Here you have robot 2. So when it rotates, either it will rotate like this. This square will be fed to the first robot, and the circle will be fed to the second robot. Once it rotates, the circle will be fed to the second robot, and the square will be fed to the circle will be fed to the first robot, and the square will be fed to the second robot. Okay, the advantage is the conveyor can accommodate many robots. Carousel has limitation because it is in between two robots, so it will have limitation. Part holding devices which are used to hold the sub part in an exact orientation or a position. Okay, it is normally used in assembly line task. Most of the robots are one-handed. Okay, and have a tool in the end of the operation in any time. Work holding fixtures are needed to place sub-assembly part at workstation, and when the robot completes the manipulation task by adding a new part to the sub-assembly. So the work holding fixture is considered as a fixed tool, and it is fixed and immobile. It cannot move or reorient itself. So, for example, jigs and clamps. Okay, at the end, jigs and clamps can't change its position. So that is, for example, if a robot performs a nut tightening operation, it is screwing. So suppose a robot has already fixed up a bolt, and it is placed in a fixed tool or a computer controlled clamp. So while planning the nut fastening trajectory for the tool, the nut will be twisted. Okay, suppose the robot has robot has picked a nut, and this is a fixture in which it has to fix. So while screwing it inside, it has to actually keep into point how many turns it has to take to twist the nut into the tool roll motion. Okay, it has to take tool roll motion, and what is the adjustment it has to make inside. The approach vector must be consisting of the pointing perpendicular workspace, work surface x0, y0 plane. During the threading operation, the sliding vector and normal vector gets twisted in the threading operation. To determine the threading operation, it takes 3 seconds to roll one complete revolution. So this is how I was talking about. This is the nut, this is the bolt. It has to be clamped inside. So if the screw transform is applied to the bolt, B is equal to x raised to b, y raised to b, z raised to b as given in this. The angular displacement of the screw is defined by theta t. Theta t is equal to 2 pi by t radians. Determine the linear displacement of the screw. The tool has to slide down fast between the to reach the bolt, and the nut is turned clockwise. Okay, if the pitch of the bolt is beta mm threads, and performs one rotation in 1 second, the linear displacement will be given by lambda t is equal to t by beta t mm. If length of the bolt is bm long, so threading will be how much? T is equal to beta b t seconds. The orientation, now the position and the orientation frame. Okay, so threading will be given by thread is t is equal to what I told, tool to the base. So it is thread to the bolt. So t of t, screw lambda t, theta t and 3. So which is less than equal to bpt. Screw transformation is the product of rotation and the translation. The homogeneous transformation equation matrix which maps the bolt coordinates and the base coordinate is given by T bolt to the base. This is the identity matrix. This is the ROH rotational matrix. This is PR 0, 0, 0, 1, 0, 0, 0 and 1. Now the homogeneous screw matrix is given by, see, the rotation identity matrix, the rotation in the first, it is rotating in one coordinate, so it will be taking care as cos theta t minus sin theta t and cos theta t, and so this will be the final matrix which we get, which is equal to sin 2 pi t cos 2 pi t, cos 2 pi t by small t by capital T, sin 2 pi t by t 0, 0, 0 minus 1, h minus t p t 0, 0, 1 of t. So this is the screwing matrix. Now pick and place operation. In pick and place operations, the main and the fundamental function of any robot manipulator is to pick up the object from one position to the and place it in the another position. So and place it in another position in its position and orientation. The pick and place motions are used to alter the distributions of the part within the workspace. This operation is basically performed to used to load or unload machines from one place to the in loading and unloading machines. That is wherein we pick up something, place it in some other locations. Okay, the robot during the pick and place operations move along the path is known as trajectory in a particular time. The path taken by the robot from the pick point to the place point is called as 4 discrete points: minimal, pick and place trajectories. So pick will happen first, the lift off point pick will happen. So at the pick position, you will have something called as a lift off points. Okay, pick point is the first point in the pick and place trajectory. The coordinate frame is denoted by t raised to pick by t base. This represents the initial pick and position, initial position and orientation of the pick. This represents the initial position and the orientation of the part being manipulated. So, for example, suppose this is the object placed out here. So when I pick it, I'll have to place it somewhere else. So while picking it up, what I have is the lift. I do lift operation. So lift off points also has to be considered. While placing it out, we'll again have certain other points to be considered. So this represents the initial position and the orientation of the part being manipulated. The pick position is considered to be the center of mass or centroid, and the object is picked using approach vector r raised to 3 in which is perpendicular to the works, which is, see, this is the work. So this is perpendicular to the work surface x0 y0 plane on which the part is resting, and the sliding vector r square moving inwards closing the gripper. D pick represents the vertical distance from the horizontal workspace surface to pick the object. Okay, so this is given out. D pick. This is the gripper of the robot, which is connected to a what? It will be connected to the tool roll. Okay, so now to pick this up, it has to contract. The two grippers have to contract itself to the position it reaches the edges of that block. Then it has to exert a force and up. So the distance for which the tool grippers will lift will be given by D pick, and this is the distance D pick out here. Okay, now consider the lift-off points. The second point of pick and place trajectory is the lift-off point. The tool coordinate is denoted by lift to the base. See, earlier it was pick and base. Now it will be lift and base. Lift-off point is near to the pickup point that the robot will move before the reach down to pick up the part. The lift-off point is an intermediate point and is inferred from the pick tool. The tool orientation at the lift-off point is identical to the tool orientation at the pick point. While picking it up, see, if this is the tool gripper, I have to compress my fingers to the distance to pick, so the tool orientation doesn't change out here. Only the distance changes out here. So that is for distill to written out that the tool orientation at the pickup and lift off will be remaining the same. Okay, only the distance of the tool of this object from the base changes. Okay, so the tool orientation remains fixed as the tool moves from the lift off to the pickup point, to the point which you pick up. Suppose if you are picking up to this distance, so this will be your D pick. So if you are picking up to this distance, it will be your D pick. If you are picking up to this distance, now this distance will be your pick. Okay, so pick distance is the distance to which your arm or the tool picks up the object. Okay, to position vector. So how will P pick position point P minus VR pick I3 by 1. So if you place and set, now pick ho gaya, you have to pick and place. So you have to first consider the pick. Fine. You have to calculate the distance. You have to write the equation for the lift of frame points. Now, what is the next thing? You will pick it up from one place and go ahead for a certain distance and then place it. Okay, so while placing, you can't throw it like this. You have to place it properly to the given location. So placing down has set down points. Okay, pick has lift points, so placing will have set down points. Okay, so how many things we have? We have lift off points, we have placing, and we have set down points. So this completes the operation. So place is the third point in the pickup trajectory. The coordinate frame is defined by place base. Okay, and it is represented by R place. So D pick is equal to D place. The distance of pick from the base, how much height you have picked is equal to result which you place it down. So d peak will always be equal to d place. You don't have to calculate it again. Okay. Okay. See, this is the complete diagram. You are picking. It is see. This is the place position. So your d pick will always be equal to d place. So the constraint of pick and place position is d peak is equal to d place. The object is picked up from the workspace work surface and placed touching to the work surface. If d place is less than d peak, the robot as a result the part between the two fingers and objects or part falls down because of the gravity. So now, what it is, what has set down point is doing to what is the importance of the? We'll see what is the importance of the set down point. The last point in the pick up and place trajectory is the set down points. The set down points is denoted by T set to the base. It is the point near the place and that moves the robot to before an attempt to made it place the part. The set down point is an intermediate point that is inferred from place to the place point. Okay, from the part to the place point, and that is given as is computed as r place r p place minus v r place I cube 0 and 1. Okay, so this is the entire pick and place. See, pick from one place, find motion, lift off, gross motion via gross motion means link 1, you are performing gross motion 2, via link 2, and you are set down using a fine motion and placing it. The sequence of motions needed place operations with minimal 4-point trajectory. If feeder, conveyors and cursors are used to present parts of the robot, pick and place surfaces are at different level or the different orientation. If this is the complications are added to it. If it is a pick and places at different orientation, different location, different level, that time you have certain problems. If the workspace consists of obstacles, to avoid the collisions, one or more wire point will increase. This wire point, see, we have wire point 1 here, we have wire point 2 here. Suppose if you had an obstacle in between, your wire points will increase and can be inserted between the lift and set down point. Speed variation. For a robot to complete a particular task, speed is most important. The robot controller has been designed in such a way so that it controls the speed. The gross motion between the lift off and the set point can be carried out at speed of efficiency. The fine motions near the two ends of the trajectory should be carried out to reduce at the reduced peak. See now. We'll see summary. If the lift off is gross, speed is fast. If it is pause, it will be fine and equal to 0. If it is peak, it will be fine and equal to the motion will be fine and the speed will be very slow. If it is grass, speed will be fine and it will be slow. If it is a wire point, it will be grass and it will be fast. Now set down point will be grass and fast. So this is how you will have various, this is a table showing up path sequence and the pick and place moments in between. Now, if it is a continuous part, we had some works are wherein we pick and in the desired location or desired orientation along the specified thing. Now see, you have to be very specific, because this kind of continuous work is done normally, in automotive companies. Suppose if you have to paint a part red or a part of a car. Suppose if you have to paint the bumper silver and the car red. So only the bumper part should be completely sprayed silver, and after that the upper part of the dashboard should be red. So that line should be, that tool orient should be so specific that the arm orientation should be so specific that while it paints the bumper, it should paint the bumper only. It should not paint any other part of the car. So normally it is this kind of continuous motion is used in spray painting, arc welding, and inspection parts. Okay, so the block diagram is like this of the continuous path motion. This is the work done, differentiated trajectory, path planners. Okay, continuous path can be calculated for any axis, that is 5 axis, 4 axis, 3 axis articulated robot. Now interpolated motion is a type of motion executed by point to point robot. Okay, in many instances the path is not completely specified. Knot paths are such as knot points. This is the knot points. Wire points, or there will be many, to reach from start to end, there will be many wire points. Okay, so trajectory